All right, hello everybody. Welcome to the next video in our AP Chemistry video series. A couple of things to note before we get started here. Number one, this video is actually going to be broken up into two parts. What I mean is the slides portion of the video will not just be a single video. There's going to be a part one and a part two. Part one is going to cover a lot of the sort of background knowledge that we need, and then the second part is going to sort of cover more of what the actual learning objective is for this topic. And then there will be a problem-solving video as well. So we're still in Unit 1, Atomic Structure and Properties, Topic 5, Atomic Structure and Electron Configuration. Like I said, we are going to be talking about mostly background knowledge here in this first video, so I'm actually not going to reference this learning objective quite yet. I'll do that in the second video. Our table of contents for today, we're going to be covering the first three topics here in this first video, the next three in the second video, and then, like I mentioned before, there will be a problem-solving video at the end, the third video. Okay, so let's get started. So before we really get into it, I wanted to cover some vocabulary. These are things that these are words that you've probably heard before, but we need to make sure that we're all sort of working with the same set of vocabulary before we really dive in here. So the first term I want to bring up is quantum. Okay. So what is a quantum? A quantum is a discrete quantity of energy. All right. Let's make sure we know what discrete means. All right. Now I know with my class, my advanced chemistry classes, I do talk about the difference between discrete and continuous. You may not have heard this before, so this will be some good review if you had me last year, or this is just important information for you to know if you didn't. So what does discrete mean? Well, discrete means apart or detached from others, separate or distinct, whereas continuous is sort of the opposite of discrete. It means forming an unbroken whole without interruption, right? So a quantum is a discrete quantity of energy, right? And why is this important? Okay, well, much of what we're going to be doing today in this video, right, part one, is we're going to be sort of telling a story, right? How did we arrive at sort of our modern model of what an atom looks like, and specifically, how did we arrive at our modern model of how electrons behave? Okay, and so where this story basically starts is with a guy named Max Planck. Down there at the bottom, you can read along with me. It says, in 1900, Max Planck discovered that the energy of a system can only be gained or lost in discrete amounts, right? Distinct quantities. These packets of energy have since been referred to as quanta. Okay, so quanta is the plural of quantum. In other words, energy was discovered to be quantized. Okay, now we're not going to get into the details of how he discovered that. Let's just assume that he's right. Okay, energy is not a discrete thing. Or excuse me, energy is not a continuous thing. It is a discrete thing. Okay, so instead of energy being available in amounts, in any amount, right, energy is actually only available in our universe in discrete packets or discrete amounts, okay, which are referred to as quanta or individual quantum. Okay. Okay, one other thing we need to talk about is the atomic spectrum of hydrogen. So take that information about quantum and quanta, sort of put it on the back burner for just a moment. Let's talk about what's going on here, and then we're sort of going to put those things together as we move forward. Okay, so once again, I said that we're sort of telling a bit of a story. So one other aspect of this story is that around the same time, okay, so in the around 1900, like the turn of the century, some work was being done with spectra. Okay, so spectra, like the visible spectrum, or different spectra of light, is just a way to sort of analyze what light is made of. Okay, and What you guys are probably aware of is that if you take white light and you break it apart through a prism, you get all of the different colors of the rainbow, right? And this, you can see here, this is Roy G. Biv written backwards: red, orange, yellow, green, blue, indigo, violet. When you take white light, you pass it through a prism, you get all of these colors in a continuous spectrum, right? So if I go back to the previous slide, that spectrum forms an unbroken whole without interruption. Okay, so you get all of the different colors or all of the different wavelengths of light from red all the way to violet. Okay. Now, what's important for us on this slide is what we see here in this second setup here. Okay, so instead of looking at white light, what a lot of physicists were doing at around this time, right, 1900, is they were looking at the visible spectra for individual elements. Okay, so this down here shows us a setup that involves hydrogen. Okay, so what's actually going on here is that this is called a discharge tube. There's gaseous hydrogen inside of here, and there's not like an actual wire. It's kind of a complicated thing here, but basically what's going on is we're passing some electricity through the hydrogen. Okay, it's not like we're igniting or burning the hydrogen. There's no chemical reaction going on, but we're providing the hydrogen gas with some excess energy and observing what happens. So when you do that, the hydrogen gives off light. Okay, but when you analyze that light, we do not see a continuous spectrum. What we see instead is discrete wavelengths of light being produced, discrete colors being produced by the hydrogen. Okay, now if I move my mouse down here to the bottom of the screen, it sort of covers up the numbers there, so I'm going to move this away. The wavelengths of light that are produced when electricity passes through that hydrogen gas are those four colors that you can see down there: 410 nanometers, 434 nanometers, 486, and 656. Those wavelengths correspond to different colors. So that's interesting, right? You might be thinking to yourself, well, why? Why does hydrogen only produce those four colors? Why does it only produce 4? Why not 5 or 6 or 20? And why is it those specific colors, right? Well, it gets even weirder when you consider the atomic spectra of other elements. Okay, and I have some over here. They're not labeled because it's not really important, which elements are which here. But as you can see, with different elements, we get different line spectra. Okay, different colors that get produced. So scientists were grappling with Max Planck's discovery that energy is quantized, right? It comes in specific discrete packets rather than just being any amount. And they were observing line spectra of different elements, seeing that hydrogen, for example, only produces 4 colors, only 4 wavelengths of light, nothing else. So, one person who, like I said, we're sort of telling a story today. One character in our story took some of this information together and did a lot of work with it. His name was Niels Bohr. He's a Danish. He was a Danish physicist doing his work in the early 1900s. He took the information that we sort of just talked about and synthesized it together into the first quantum model for the hydrogen atom. Okay, and I want to spend a little bit of time talking about what I mean by this exactly. Okay, so let me go all the way back here. Prior to 1900, scientists thought of energy as being a continuous type of thing. Okay, you could have any amount of energy. Max Planck discovered, though, that that is not actually the case. Let me show you this equation here. Okay, let's talk about the variables really quickly. E stands for energy. V, or the Greek letter nu, stands for frequency. And then this right here, the Greek letter lambda, stands for wavelength. As you can see with this right portion of the equation, the frequency and the wavelength are sort of tied to one another. You can calculate the frequency by taking c, which is the speed of light, and dividing it by the wavelength. Okay, so just for our purposes for today, frequency and wavelength are, I mean, they are different, but they're kind of a similar type of term. Okay, all right, so let's look over here on the left side. What Max Planck discovered was that energy, the amount of energy in, say, one of these packets, right, that he discovered, is equal to h, which is Planck's constant. Okay, it's not really important what that actual number is. Okay, it's equal to the amount of energy is equal to Planck's constant times the frequency. Okay, what this says, right, is that regardless of your frequency of light that you're observing, the change in energy, right, like let's say the difference between this yellow and this bluish color, it depends on Planck's constant. Okay, let me see if I can rephrase this just a little bit. What Planck discovered was that energy really is broken up into bits, okay, and the smallest bit is sort of bound by this Planck's constant. Okay, think if you put the number 1 here, right, for the frequency, and then you put the number 2, right, the change would just be based off of what h actually is, right? So let's sort of take that idea that energy really does come in sort of these packets, and let's combine that with what we actually observe with hydrogen, right? We see these discrete frequencies or these discrete wavelengths, and then let's think about what atoms are, right? Atoms are and let's talk about a hydrogen atom specifically, right? Because that's what Niels Bohr actually really did look at first. A hydrogen atom is a proton and an electron, right? And hydrogen is what was in this tube, right? So what Niels Bohr really wanted to do is he wanted to explain what was going on here, right? Why did hydrogen, with its 1 proton and 1 electron, only emit 4 colors at these 4 specific locations? Why? Why did that happen? So, what he deduced through some mathematical calculations, through his observation and analysis of the evidence, was that in a hydrogen atom, the electrons could only move around in certain discrete circular orbits. Okay, so instead of the electrons being able to sort of freely move around however they wish, they are sort of bound to certain energy levels or levels of energy. Okay? Using the data from the line spectrum of hydrogen, Bohr was able to assign these orbits energy levels. These energy levels can be expressed according to an equation of his own derivation. I'm not going to get into the details of this equation just yet. In fact, what I'd rather do is show you some diagrams here. So right here, part B, I guess, we have this big drawing of sort of the Bohr model of a hydrogen atom. Okay, what's not shown here, right where my cursor is, that would be the proton or the nucleus of the hydrogen atom. Okay, now let's think back to some of the things that we've talked about in previous videos. Protons are positively charged. Okay, electrons are negatively charged. Opposites attract. So the proton and the electron inside of a hydrogen atom are attracted to one another. That means that if the proton is here in the center, the electron we would tend to think that the electron would want to be as close to the proton as possible, right? So it would perhaps reside in this first ring here. Okay, what Niels Bohr is proposing is that instead of the proton being, instead of the electron being able to be anywhere, okay, based on this line spectra that we observe, right, these specific colors, right, and it's always these colors, based on that, he's proposing that the electron is only allowed to be in these specific rings, which are specific distances away from the proton. Okay, what's actually going on in this line spectra situation here, this phenomenon, is that when the hydrogen gas absorbs the energy from the electricity, it's the electron that actually absorbs the energy. When the electron absorbs the energy, it becomes excited. In Bohr's interpretation, what that means is that the electron jumps up energy levels, and then shortly thereafter, the electron, due to its attraction to the proton, is going to sort of fall back down to its original state, and in doing so, it's going to release the energy that it absorbed. Okay, that amount of energy is exactly the same amount that it absorbed, and that amount of energy is then going to correspond to a frequency or a wavelength. Okay, so what really happens here is atoms of hydrogen, specifically electrons of hydrogen, absorb energy. The electrons become excited. The electrons then fall back down to their original state. In doing so, they release energy, and that energy is in the form of some color. Okay, and it's these specific 4 colors that we see every single time for hydrogen, right? This never changes. You could look at hydrogen right now, you could look at hydrogen 100 years ago, you could look at a hydrogen 200 years from now, and you're always going to see this exact same line spectra. What Niels Bohr thought that meant, and he was partially right, was that the electrons must exist in these specific orbitals. They can't just be wherever, right? If we see the exact same lines every single time, the electrons must be in these exact same orbitals in every hydrogen atom. Okay, and just to give you a little bit more detail of how this works, you guys may be familiar with the different colors of light here, right? Roy G. Biv. Violet light is more energetic than red light. Okay, so like blue, indigo, violet is sort of a more energetic color than, say, red or orange. Okay, so if we look here, when an electron absorbs a lot of energy and travels up to, say, this 5th energy level, when it falls back down, it emits a lot of energy. So it emits a sort of blue color. When it falls down a moderate amount, it gives off a moderate amount of energy, or say a moderate color like green. And then when it only falls a little bit, it gives off just a bit of energy. And so we get sort of a low energy color like red. Okay, so this is how Bohr came up with this model. All right. Now, it turns out that Bohr was onto something. Okay, now he wasn't completely correct, all right, but he was really onto something. Let me just read this for you. It says Bohr's model worked relatively well for hydrogen, the simplest of all the elements. His model and equations began to break down, however, when applied to even slightly more complex atoms. So his model, his simple model that worked for hydrogen, doesn't work all that well for like helium and lithium and beryllium and so on. So while he was onto something, a new model was needed to account for the behavior of electrons in these larger, more complex atoms. Okay. Some other folks, which we're going to talk about in some varying amounts of detail, like Heisenberg, for example, are credited with the development of the quantum mechanical model. Think of the quantum mechanical model as being kind of like Bohr's model 2.0. It's the same kind of fundamental theory, but it's expanded and applies to more situations. Okay? So, in the quantum mechanical model, electrons are thought of as having both particle-like properties and wave-like properties. I'm going to pause right there. This is really, really important, guys. Really important, okay? If you've been watching this video so far and you are feeling like you're starting to zone out a little bit, I want you to press the pause button, go get a drink of water, go take a walk, come back, okay? Because I'm going to talk about this for a few moments, and it's really, really important that you understand what I say here. So Niels Bohr sort of cracked the door, opened us up to this idea, and these other folks here, Heisenberg, de Broglie, and Schrödinger, sort of continued their work. What this says is that we have to think about electrons as having both particle-like properties and wave-like properties. All right? A particle think about things that we might say about a particle, right? Its properties. We might say its position, we might say its velocity, we might say its direction, right? So it's got a certain position and it's moving at a certain speed in this direction, right? That might be how we describe a particle. What does this mean? Wave-like properties. Well, wave, really this means kind of like energy, okay, it's like an energy-like property. Some of those properties might be a wavelength or a frequency or an energy, okay, like an amount of energy. So in the quantum mechanical model, right, which Bohr sort of started, electrons cannot be thought of as only having particle-like properties. They have to be thought of as having both particle-like properties and wave-like properties, okay? This was a huge paradigm shift, okay? A paradigm shift is just a way, it's a change in the way people see things, all right? So this paradigm shift in how physicists viewed the fundamental building blocks of nature was truly radical, okay? By the early 1900s, many physicists seemed to think that we had essentially figured everything out, right? All of nature's big problems had been solved or close to being solved. The advent of quantum mechanics, however, changed everybody's mind, okay? And we are still, to this day, right, 2020, still trying to figure out all of the details of quantum mechanics. And there's very few people who know everything there is to know about quantum mechanics. It's extremely complicated. So what we're going to be talking about for the remainder of this video, you know, it's difficult stuff, and I don't want you to feel like you have to be a master of quantum mechanics after watching, you know, like a 25 minute video, okay? Now the good news is we are going to be glossing over a lot of the mathematical details of quantum mechanics. Those sorts of things are not going to be assessed on the AP chemistry exam. You can check out the book if you really want to go into detail like that. What we need to know are the ideas, the concepts that apply to electrons and their positions in an atom, okay? So let's talk about one implication of the quantum mechanical theory, okay, as it applies to electrons. It's called Heisenberg's uncertainty principle, okay? One implication of quantum mechanics involves the position and momentum of electrons, okay? And whenever you hear this word momentum, just think velocity or speed, okay? They mean roughly the same thing. What Heisenberg's uncertainty principle says, okay, he did some mathematical analysis of quantum mechanics. It showed that there is a fundamental limitation to how precisely we can know both the position and momentum of a particle at any given time. What this means, okay, is that we essentially can't know both, okay? You can't know the position and momentum of a particle, okay? And his math goes on more to tell us that this limitation is not so limiting when talking about large objects, okay, so like a football, right? We can all see a football, right? If it's getting thrown through the air, we could say, oh, there's its position, there's its speed, or there's its momentum. But this uncertainty principle is extremely limiting when talking about smaller objects like electrons. And at the time, electrons were the smallest objects that people knew existed. So it's extremely limiting when talking about electrons. So limiting to the fact that we really just can't think of electrons as only being particle-like. We have to think of them as being wave-like as well in order to truly understand what's going on with them, okay? So, applied to the electron, the uncertainty in principle implies that we cannot know the exact motion of the electron as it moves around the nucleus in an atom. We cannot assume electrons move around in nice, well-defined orbits such as those found in Bohr's model. Instead, we must think of electrons as having probability distributions that describe where one might find them at any given time. These probability distributions are mathematical tools that we can use to help us visualize where electrons might be in an atom. This right here, part A, is a probability distribution for the electron in a hydrogen atom. The next three sentences, explain how you should interpret this probability distribution. Okay, and I think this is really, really cool. It says the best way to think about this diagram is as a three-dimensional time exposure with the electron as a tiny moving light. So imagine you had a tiny little camera and you click and hold the shutter open and you can see where that electron is, okay, over time. The more times the electron visits a particular point, the darker the negative becomes. Thus, the darkness of a point indicates the probability of finding an electron at that position. So here in this diagram, which you can see a little bit more clearly in your book on page 268, the darker regions, right, which is towards the center, as we would expect, right, if the proton is the nucleus, the electron is going to try to be as close to the nucleus as it can. The darker portion of this probability distribution is towards the center there, right? So the electron is more commonly found there than it is further out, which, and as you can see, eventually we get to just sort of white space, right, where we're very unlikely to find the electron. Okay, so that's basically what this probability distribution is showing us here. And then there's a graphical representation of that as well. All right, and all this shows us is that the probability of finding an electron is higher as you get closer to the nucleus, right? Distance from nucleus, this would be 0. This would be some large distance. You have a higher probability of finding the electron closer to the nucleus than you do when you're farther away. Okay? That's it for the first video. We're going to sort of apply this concept of probability distributions into what are referred to as electron orbitals. And then we're going to learn how to work with electron orbitals and apply that to electron configurations in the next video. All right. As I said before, I try to keep this as short as possible. This is actually my second time recording the video, so doing a bit of work here this morning. But yeah, thanks for watching and stay tuned for the next video.